Okay, so hopefully we know how to handle pointers a little bit better. Um, and if if you run across into code that has a bunch of pointers, at least you'll be able to draw it out and figure out the answer to things. So let's go back and read our book. So can't remember exactly where we stopped, but I'm just going to trust that maybe it was here because that's where the um, book was opened to, or at least a PDF. So I remember that we created a program that took in, yeah, a text file, and we constructed link lists elements of all the islands and toured them from top to bottom. And I think we added also additional islands from the text file that we had because the text file didn't have enough elements, I believe. So yeah, the one takeaway from all this is here. Dynamic memory allocation lets you create the memory you need at runtime. Runtime. So if we don't know exactly how much memory we need while we are coding, well, we can use malloc, right, to allocate additional memory or memory on the fly during when we're running our program. And when we're ready to release our memory, we call free so that we give memory back to the operating system so that we can use it in the future or let another process use it. We don't want to hold onto memory too long because that would just allow us to get into a situation where we have a memory leak where we start to consume more and more memory. We don't really have any more memory eventually down the line to consume, and then we either crash due to out of memory or something else happens. So yeah. So here's a conversation between the stack and heap. Stack and heap discuss their differences. Heap goes, "Are you there? I'm home." Heap says, "Don't see you too often this time of day. Got a little something going on?" Stack says, "Deep regression." "Oops, excuse me, just tidy that up." "What are you doing?" "The code just exited a function. Just need to free up the storage from those local variables." You should take life a little easier. Relax a little." "Perhaps you're right. Mind if I sit?" "Beer? Don't worry about the cap. Just throw it anywhere." "I think this is yours?" "Hey, you found the pizza. That's great. I've been looking for that all week." "You should really consider getting someone in to take care of this place." "Don't worry about it. That online ordering application left it lying around. It will probably be back for it." "How do you know? I mean, how do you know it hasn't forgotten about it?" "Oh, he'd have been back in touch. He would have called free." "Hmm. Are you sure? Wasn't it written by that same woman who wrote that dreadful Whack-A-Bunny game? Memory leaks everywhere. I could barely move for rabbit strucks." "Hmm. Droppings everywhere. It was terrible." Heap goes, "Hey, it's not my responsibility to clear up the memory. Someone asks me for space, I give him space. I leave it there until he'll tell me to clean it up." "Well, that's irresponsible." "Yeah, maybe. But I'm easy to use, not like you and your fussing." "Fussing? I don't fuss. You might want to use a napkin." "Belch." "What? I'm just saying you're difficult to keep track of." "I just believe that memory should be properly maintained." "Whatever. I'm a live and let live type. If a program wants to make a mess, it's not my responsibility." "You're messy." "I'm easygoing." "Why don't you do garbage collection?" "Ah, here we go again." "I mean, just a little tidying up. You don't do anything." "Easy now." "I'm sorry. I just can't cope with this level of disorganization." "Hey, you're overflowing. Take this." "Oh, thank you. Wait, what is it?" It's the high score table from Whack-A-Bunny. Don't worry, I don't think the program needs it anymore. That's funny. So the conversation is saying that like the stack will usually clean up for you, but it's very limited space. So you're going to end up stack overflowing if you allocate too much on the stack. And usually, how that happens is if you do something called recursion. Now, for the heap, every time you allocate memory, it is the program's responsibility to free it up afterwards. If you don't free it up, it's just going to stay there for the duration of the program's lifetime. Um, what else? Oh yeah, and this last statement here is like, don't worry, I don't think the program needs it anymore. There could be chances where you allocate memory and then you might have some other function that doesn't like care about this memory, or no, you have some other function that wants to use memory. It could end up writing stuff over that memory. And even if you care or don't care about that, you're still able to do that because in C, all that's kind of unprotected. So, yeah. So, why is a heap called the heap? Because the computer doesn't automatically organize it. It's just a big heap of data. What's garbage collection? Some languages track when you allocate data on a heap. And then, when you're no longer using the data, they free the data from the heap. Why doesn't C contain garbage collection? C is quite an old language. When it was invented, most languages didn't do automatic garbage collection. That's because it could have used up too much CPU. Back then, CPU time was very, very precious. Let's just say that because things were just slower back then. Okay, so I understand why I needed to copy the name of the island in the example. Why didn't I need to copy the opens and closes values? The opens and closes values are set to string literals. String literals can't be updated, so it doesn't matter if several data items refer to the same thing. Does stirred-up actually call the malloc function? It will depend how the C standard library is implemented, but in most of the time, yeah. So that's the one thing that happened last time I got tricked, right? Like the stirred up implicitly calls malloc. So when you call stirred up and you get back a pointer, which is I think the clone of the string, you have to remember as a developer to call free on that string in some cleanup function. Otherwise, that string value is going to leak. Excuse me. That string value is going to leak all over the place. It's just, take up memory. Do I need to free all my data before the program ends? Generally, you don't have to. The operating system will clear away all of the memory when the program exits. But that's a caveat, like when the program exits. But as long as your program is still running, if you're not freeing memory, then there's a chance that it will just continue to grow because you're using more. You're going to malloc all over the place, right? So it's good practice to always explicitly free anything you've created. Cool. So dynamic data structures allow you to store a variable number of data items. Okay, yes. So linked lists, you can add many elements. As long as they all point to each other, you can get back to them. A linked list is a data structure that allows you to easily insert items. Dynamic data structures are normally defined in C with recursive structs. A recursive struct contains one or more pointers to a similar struct. So I think what they're saying is that you have to remember, even if you did something like type def, my type def struct, my struct, and then you have like properties here, you'll still have to do something like struct, my struct. This one's important, and that refers to the alias here. That's what we mean by recursive struct. So you have a struct of the same type within that struct. So Let's see. The stack is used for local variables and is managed by the computer. The heap is used for long-term storage. You allocate space with malloc. The size of operator will tell you how much space a struct needs, and data will stay on the heap until you release it with free. What's my data structure? So you've seen how to create a linked list in C, but linked lists aren't the only data structures you might need to build. Below are some other example data structures. See if you can match up the data structure with the description of how it could be used. So this one is, I can be used to store a sequence of items and I make it easy to insert new items, but you can process me in only one direction. Of course, that's a linked list right here. Each item I store can connect up to 2 other items. I am useful for storing hierarchical information. Oh, that's a tree right here, binary tree. I can be used to associate 2 different types of data. For example, you could use me to associate people's names to their phone numbers. That should be like a map like this here. Okay. Then each item I store connects up to 2 other items. You can process me in 2 different directions. This one right here for sure. So that's pretty easy. So you know your data structures. So a map goes here. Associate people's names. So I hear associate. So I hear a map or associative array. And then doubly linked list is you can process me in 2 directions. And then this one's hierarchical information. This one is easy one, only one direction, makes it easy to insert new items because you can just insert items in between. So yeah. Data structures are useful, but be careful. You need to be careful when you create these data structures using C. If you don't keep proper track of the data you are storing, then there's a risk that you'll leave old dead data on the heap. Over time, this will start to eat away at the memory on your machine, and it might cause your program to crash with memory errors. That means it's really important that you learn how to track down and fix memory leaks in your code. I see where this is going. Okay, so we're gonna have to learn a new tool. So, top secret. Federal Bureau of Investigations, United States Department of Justice, Washington, D.C. Okay, from J. Edgar Hoover, Director. Subject, suspected leak in government expert system. Our Cambridge, Massachusetts office advised that there is a suspected leak somewhere inside the new suspicious persons identification expert system, which is abbreviated as SPIES. Our sources and informants familiar with software matters advise that the supposed leak is the result of shoddy coding by persons or persons unknown. An informant who has furnished reliable information in the past and who claims to be close to the people concerned has advised that the leak is the result of careless management of data in the area of memory known to the hacker fraternity as the heap. You are hereby given access to the expert system source code and have, by my order, been given access to the full resources of the FBI Software Engineering Lab. Consider the evidence and analyze the details of the case carefully. I want this leak found and I want this leak fixed. Failure is not an option. Very truly yours, J. Edgar Hoover. Okay. All right, so we're going to have to investigate stuff. Memory leak, most likely. Is it right? So, yeah. Exhibit A, the source code. What follows is a source code for the Suspicious Persons Identification Expert System, or SPIES. The software can be used to record and identify persons of interest. You are not required to read this code in detail now, but please keep a copy of your records so that you may refer to it during the ongoing investigation. So really, it's just just a bunch of includes. Defined a struct node with character pointer. So pointer to a character called question. So that's like a string. A yes no struct node. So it's a recursive one. So if I'm guessing if a person chooses yes, there's leads you to another question. If a person chooses no, it'll lead you to another question. And then here's a yes no function. Given some question, let's see. Oh, get an answer. If it's yes, then it's return true in this case, and that's just checking the first character of this 3-character answer. And I think then basically it's taking into consideration the FKS3, the null terminator, right? The null terminating character. So yeah, okay. And I guess new line is considered too, so that's why. So it's Y, new line, null terminating character, or N, new line character, null terminating character. So those are 3 characters. Then we'll have another function that creates the node based off the question, the string here, pointer to a character. We're gonna malloc the size, basically allocate some memory where it's the size of a node, so a node struct. So basically, we don't know how big the question is, but that's going to be a pointer to a character, so that's 8 bytes, and then another whatever bytes this is. So in this case, this is a pointer, so it's another 8 bytes, and this is a pointer, so it's another 8 bytes. So it's 24 bytes. So yeah, 24 bytes for one node because they're all just pointers. So 888. So we'll malloc that, and then we'll fill the question with stirred up, which is going to create. So the tricky part here is that it's going to clone that string into a new pointer, but this is something that we have to remember. We have to free it ourselves. We'll initialize the no pointer to a different struct as null. Same thing with the s to a different struct as null, pointing to null basically. So if we take a look at like our memory map, for example, what we're doing here with this create code is given, I want black, given some memory, we'll have something like 100, 101, 102, 103, 104, 105, 106, 107. So we're going to create a pointer, n. So be basically node star n. And that's going to point to some, I guess, thing in memory. And we had said there's 3 things. So let's just call it 104. Starts at 104. So 104 here. And this is the allocated memory. We're going to stir up the question. So we'll say this is going to be the string. So, we'll probably say, y and no terminating character. And we'll say that starts at like 101. So that could be char star question. So that 101 points to here, which gives us our string. And then we'll have no, which is basically null. And we'll have yes, that's basically null. This case, that is pretty much 0, 0. Okay, so that's how it could look like. So we'll have like a main pointer here that represents the node pointer struct, a pointer to a struct, a node struct, and that struct data starts at 104. And then from here we have the question, another pointer to a node somewhere. It could be like right there where it has question, stuff like that too, and another one somewhere in memory with yes. But right now it's just pointing to null, so 0 memory address. So we return that pointer, so we return this pointer here. Okay, then we'll have a release function that just takes in the node and then it releases. So it'll recursively call release on that specific node. So we'll call release again, and then the no node will be right here, and it does the same thing again. Until basically, I guess, it's wrapped under an if condition. So if we get a null condition, for example, because these nodes are initialized to null, we won't run any of this code because null is 0 and 0 is a falsy value. And I noticed here that they also freed question, so that's good, and they also freed a node at the end. Okay. Sure. All right. So here is the main code here. We'll have a buffer of 80 characters, a buffer of 20 characters, so an array, two arrays. Then we'll create a node, called start node. So create, again, going back here, we'll just create a pointer to some struct allocated memory, about 24 bytes, I guess. And then we'll create recursively, like with the start node's no, we'll create another node that leads to another question, in this case Loretta Barnsworth, and that's basically, I can tell that questions and answers are just seen both as questions. And then that node, right, even though it has Loretta Barnsworth, the no and the yes will still be null, so it doesn't lead anywhere. So we're taking a look at something like this, for example. Does suspect have a mustache? Then there's a no pointer, and then there was like a yes pointer. And then basically the no pointer was something like Loretta Barnsworth. And then this yes pointer was it Vinny the Spoon? But within each of these nodes, they had been initialized with null, null. Same thing with this one. No, null. Yes, here is still null. Okay. Now, this one's a big one. Okay, so we have a current node here. Now the current is going to be the start node. I'm glad I drew that out. So that's current. Okay, and then while true, if yes, no current question, what does yes, no do again? Let's go back up. Yes, no. We'll print the question. Oh, and ask the user yes or no. Okay, sure. So if the user says yes, meaning that what is it? I guess if current goes to yes. Oh, okay. So if the user had answered yes and we also have a yes node, then we move the current to be now the yes part. Okay. Else, if there is no yes node, we'll just take the other node and assume that that's the suspect. So it could be one or the other. And if the current if yes no was answered as no, falsy value, we'll take this one right here and set current to be no. So just right away current is going to be this one, for example. Okay. So if I answered the suspect have a mustache, and if there is something here, current will go to yes. And then otherwise, if I said no, well, okay, here, Loretta Barnsworth, sure. And then else, make a yes node with a new suspect name. Okay, so otherwise, if it's something, if there is no yes no, what is yes no? Oh, okay. That's really confusing. So if they didn't answer that, they'll be prompted to create a new node. Who's the suspect? Okay, so we create a new node here, and then with the suspect's name, then we'll set the current yes pointer to be the yes node, and then we'll make the no node a copy of this question. Okay, and then we'll point the no node to there. Okay, so else if we don't have a question. Okay, great. Okay, or like no, we don't have choices. So then give me a question that is true, but for I guess the suspect, but not for the question. So question here, and then it'll stir up that question. It'll stir up the question. So that is interesting. Sure, that's an interesting one. Okay, while it's going to ask after each iteration of doing this, do we want to run it again? And then otherwise we release start node. Okay, sure. An overview of the SPY system. The SPY's program is an expert system that learns how to identify individuals using distinguishing features. The more people you enter into the system, the more the software learns and the smarter it gets. The program builds a tree of suspects. So it is a tree. The yes, no are kind of like left, right pointers. The program records data using a binary tree. A binary tree allows each piece of data to connect to two other pieces of data like this. Okay. Has a mustache? Yes. Vinny has a mustache. No, Loretta doesn't have a mustache. Okay, great. This is what the data looks like when the program starts. The first item or node in a tree stores a question. The suspect sorry. Does the suspect have a mustache? That's linked to two other nodes. One if the answer is yes, and another if the answer is no. The yes and no nodes store the name of the suspect. Okay. The program will use this tree to ask the user a series of questions to identify the suspect. If the program can't find the suspect, it will ask the user for the name of the new suspect and some detail that can be used to identify him or her. It will store this information in the tree, which will gradually grow as it learns more things. Sure. Okay. Oh, in place of it. Okay, great. This is what happens if the agent compiles a SPY's program and takes it on a test run. So, who's a suspect? Does the suspect have a mustache? No. Is it Loretta Barnsworth? No. So, who's the suspect? Hayden Fantucci. Give me a question that's true, but not okay. True for Hayden Fantucci, but not for Loretta Barnsworth. Okay, so if we're like deep in the tree, we have nothing left. We're gonna ask to create a new node, and I guess that was this case here, right there. Okay. Does the suspect have a mustache? No. Has facial hair? Yes. Then we say Hayden Fantucci. Is it? Yes. Suspect identified. Great. Run again. Yes or no? Okay. So the first time through, the program fails to identify the suspect, Hayden Fantucci. But once the suspect's details are entered, the program learns enough to identify Mr. Fantucci on the second run. Pretty smart. So what's the problem? Someone was using the system for a few hours in the lab and noticed that even though the program appeared to be working correctly, it was using almost twice the amount of memory it needed. Okay, I need to answer stuff. Cool. So that's why you have been called in. Somewhere deep in the source code, something is allocating memory on the heap and never freeing it. So now you could just sit and read through all the code and hope that you see what's causing the problem. But memory leaks can be awfully difficult to track down. So maybe you should pay a trip to the software lab. Okay, software forensics using valgrind. So valgrind is a tool that allows us to track or trace memory leaks. Okay, it can take an achingly long time to track down bugs in large complex programs like spies. So C hackers have written tools that can help you on your way. One tool used on the Linux operating system is called valgrind. Valgrind can monitor the pieces of data that are allocated space on the heap. It works by creating its own fake version of malloc. Okay, so it traps malloc and gives a different implementation. It's probably like enhances it or something. When your program wants to allocate some heap memory, valgrind it will intercept your calls to malloc and free and run its own versions of those functions. The valgrind version of malloc will take note of which piece of code is calling it and which piece of memory it is allocated. When your program ends, valgrind will report back on any data that was left on the heap and tell you where in your code the data was created. Okay, so prepare your code, add some debug info. Um, okay, you don't need to do anything to your code before you run it through valgrind. You don't even need to recompile it. But to really get the most out of valgrind, you need to make sure your executable contains debug information. Debug information is extra data that gets packed into your executable when it's compiled. Things like the line number in the source file that a particular piece of code was compiled from. If the debug info is present, valgrind will be able to give you a lot more details about the source code of your memory leak. Okay. So to add debug info in your executable, you need to recompile the source with the -g switch. I thought it said that we didn't need to recompile it. You don't even need to recompile. That's so confusing. So gcc-g spies-o spies. Okay, the -g switch tells the compiler to record the line numbers against the code it compiles. So, okay, let's actually, before we do that, let's actually type up the program so we can run it ourselves. And it's practice too. So, let's create a new folder called spies. I think we'll just type this and then I have to go soon, so spies. Just trying to program as much as possible. So, okay. Include sdio.h, include sdlib.h, include string.h, type def. So we're going to find our struct node. That's going to have a pointer to a character called question. It's going to be a pointer to a node struct node struct called no. Same thing. So it's a recursive struct. So already we know it's kind of like a tree or a linked list, things like that. And then we'll have a function called yes, no, pointer to a character as an argument. Then we'll define a string. So basically a pointer to a character of 3 characters. So I'll buffer that, printf. Ask the question, yes, no. That's a good template. Question as an argument. fgetS, answer 3, cdn. Then we'll return answer, basically is the first character similar to what, or exactly y. Then that's a yes, y is a no. Then we'll create a node, have a function to create a node given some question. Then we'll say node n. It's gonna allocate some memory with malloc, size of node. Okay. Then n question is gonna be stirred up. Question. Then no is gonna be null. And pointing to yes is going to be null. Remember, when the arrow notation allows us to not have to, like, given some pointer to a struct, it doesn't have to make us destruct dereference the pointer to a struct to be a struct first, and then call the dot. It's just like a one-shot way of doing it. So we'll return n. So return that pointer to a struct. Then we'll have a release function. If n, then we'll say if n is no, we'll release n no. So we'll release that node that points to no. If yes, so meaning that we have a yes node, we'll release n yes. Then if we have a question, if n question, we'll basically free that because it's not recursive anymore. Just free the question right away. These two are recursive. There are other structs that we need to take care of down in the tree. Then we'll free the node itself. Cool. All right, next we'll have this big main function. Okay, we'll have a buffer. Looks like another buffer. One is 80 characters. The next one is going to be 20 characters. Then we'll have a pointer to a struct that serves as a start node, so like an initial node. Create the suspect have a mustache. Okay, so no question marks there. Then we'll have start node no. Create Loretta Barnsworth. Then we'll have start node yes. Create Vinny the Spoon. Then we'll have a pointer that serves, so a pointer to a node, a struct basically, called current. Then we'll have a do while loop. We'll figure that out later. We'll fill it in. So do current equals start node. So basically do while means to at least perform the iteration once and then check to see the condition is true so that we go again. So we'll always initialize current to be start node, and then we'll have an infinite loop if yes, and that's like the inner, that's like the question asking part, right? And then the outer while loop is going to be, I guess I'll just do that. It's going to be the yes, no, like continue, like do you want to run again after you, I guess I'm going to call this a game after you played the game. So we'll just also release start node here and then return 0. So let's finish the inner loop. It's kind of messy code, to be honest, but I guess it's C. That's what we're getting ourselves into. So current question, if current yes, this will allow us to debug at least. Current equals current yes, and else we're gonna have printf suspect identified. Break. So break out of the loop. And I think that's it. The next one is going to be else if current no. Okay. Then current is going to be current equals no. Else we're going to have to add nodes. So that looks like that. And we'll say make the yes node the new suspect name. Then we'll say printf who's the suspect, and then we'll have some space here. Then if get s, it's going to be suspect 20 SDN. Then we're going to create the nodes for it. So node yes node. Then we create suspect. So hit the suspects. So that's like the main name, and then it's going to have a yes no pointer. So current yes is going to be the yes node. Current, so we're also going to make the no node. Make the no node a copy of this question. Node. Huh. Node. Node. Create current question. So allocate more memory. Current no is no node. And then replace this question with a new question. Interesting. And F is gonna have was it give me a question that is true for that person but not for the other person. Then we'll have suspect current question. Then we'll say F get S question 80 SDN. Then we'll say current question. It's going to be stirred up again. Then we'll break. Alright, that's a lot of code. Alright, so I'm going to just try and compile it and run the example once, and then I think we're going to call that a day. So GCC may not see. Ooh, typos. So we have, first of all, in line 56, we have, okay, typo in print. So I guess line 56. We're here. And what else do we have? We'll have, let's do this. We'll have comparison between a pointer and an integer. Really? A pointer to an integer. Character. Oh, I'm in the wrong one. I'm like this one right here. Answer 0, character, integer. So that's a warning though. Okay. And then the other one is fgetS from incompatible pointer type. Interesting. Wonder why they decided to let us do all that. Oh, because I have a pointer here. That's why. It was not a pointer to a character. Oh, okay. Let's see what happens. Perfect. Okay, so does the suspect have a mustache? Let's test this. Does the suspect have a mustache? No. Loretta Barnsworth? No. Who's the suspect? Hayden Fantucci. Okay, given but not for Loretta Barnsworth. Has a facial scar. Okay, run again. Yes. Does the suspect have a mustache? No. Has facial hair scar? Yes. Hayden Fantucci. Yes. Suspect identified. No. Okay. Cool. So I would say that it's good enough for today. I'm getting tired from my work day, so get add, get commit, and we'll continue on tomorrow. Spies. Okay. All right. See ya.